Hello, welcome back to Mech 416 and Mech 816. In this video we are going to go through an example problem for the elastic wave. I've written this on the screen already. We are given a string that is fixed on each side with no external forcing, and we're asked to determine the modes of vibration for the string shown. So just a quick note, the modes of vibration have two things. They have natural frequencies. So first they have natural frequencies, which are the square root of the eigenvalues. So if you hear the term eigenvalues, you should know that they are the natural frequencies squared. And then the second thing that a mode of vibration has is a mode shape. And in this class, in this context, these are also the eigenfunctions. So eigenfunctions and mode shapes are the same thing, and they're used interchangeably in this class. So given this problem, the first thing we need to do is write down what the governing equation of motion is. So our equation of motion will be u, let's say m times u tt, and then this is equal to t u sub xx. In this case, there's no forcing, so we don't need to add the forcing term, and then this is valid for x greater than 0 but less than L, and for t greater than 0. At this point we should then also add in the boundary conditions. This is a fixed string, so we'll get u of 0 comma t is equal to u of L comma t, and then they're both equal to 0. And then we also need some initial conditions. So the initial conditions, we'll just use generic ones. We'll say u of x comma 0 is equal to a function g of x, and u sub t of x comma 0 is equal to a function h of x. Okay, so once we've defined this equation of motion, we're now ready to go and solve it, or you apply the method of separation of variables to find the mode shapes governing the system, or the modes of vibration. When approaching this problem, we're always going to use separation of variables, and what that means is that we're always going to set, let's say always set u of x comma t equal to some function psi of t times a function phi of x. So psi of t covers what happens in time, and in this class we're not so much going to study that, at least for the elastic wave. When we get to acoustic waves, we will look at that a little bit. But we're primarily going to be focused on the function phi of x and trying to find its solutions. So like I said, psi of t, this is for time, say time solutions, and then phi of x is what governs the spatial solutions. And let's actually change that to temporal solutions. We want to use the right language when discussing these problems. Okay. So at this point, we're always going to substitute in this equation. So we're going to substitute in u of x comma t equals psi of t times phi of x into our equation of motion. And useful to do each side separately. So we'll get, let's say, u sub tt. This will be equal to psi double dot times phi, and the double dots here, or the dots, represent derivatives with time only, with respect to time only, not with respect to space. And then u sub xx is equal to psi times phi double prime. So the primes represent derivatives with respect to space only. Okay, so we said that this was a derivative with respect to time, and then a prime is a derivative with respect to space. And they're total derivatives because we're taking them derivatives of functions of a single variable rather than a function of multiple variables. Okay, so if we go ahead and plug this in, we will get m times psi double dot times phi is equal to t times u, t times psi times phi double prime, and let's go ahead and divide by m and get that psi double dot times phi is equal to c squared times psi times phi double prime, and here c squared is equal to t over m, which is our speed of sound in this string. From here, we are going to divide by psi times phi. Which will then lead to the following. We will get that psi double dot divided by psi must be equal to c squared times phi double prime over phi. And here we now have two functions of different independent variables that are equal to each other. And the only way that can be true is if both of them are equal to the same constant. And so you can say that this is minus lambda or minus omega squared. And so lambda here is what we would call the eigenvalues. And then omega is our natural frequencies. And thus, we find that omega must be equal to the square root of lambda. From here, we will consider the left-hand side and derive a differential equation for psi. Then we'll consider the right-hand side and compute and extract a differential equation for phi. So by doing that, we will find that psi double dot plus omega squared psi is equal to 0. And we'll get that phi double prime plus the quantity omega over c quantity squared times phi, that is equal to 0. And we're always going to get these two equations unless we have something special going on, such as the string subjected to gravity, which you would not be expected to deal with on like an exam. You would expect it to only deal with the standard wave equation on an exam, such as this. And what that means is that you can really go from the equations of motion and then skip all the way down to here. And so the only time you can't do that is when you have something weird going on, like the string subjected to gravity. But anytime you have a standard wave equation, you can skip ahead like this. Okay, so we can actually immediately solve the psi equation, although we're not going to really do anything with it, but we can solve it. So psi of t must be equal to some set of constants, and say c times the cosine of omega t plus d times the sine of omega t. We're not really going to do anything with that, but we can solve it. In fact, anytime you have this second order ordinary differential equation, you can immediately write down the solution as being a sum of a sine and a cosine term. What we're interested in here is really this phi equation. And we can write this then, its solution as phi of x as being equal to, let's say, r times the sine of omega over c x plus q times the cosine of omega over c, omega over cx, and that is the general solution to that phi equation. We now want to find the unique solution or solutions by applying the boundary conditions. And by applying boundary conditions, we're going to find what are known as the mode shapes. So the solutions to this second order differential equation for phi of x that I'm now boxing the laser, the solutions to this equation are the eigenfunctions, also known as the mode shapes. And so we need to find both the omegas and phi of x in order to find the normal modes of vibrations. So we need to find the natural frequencies and the mode shapes or eigenfunctions. Okay, so let's write that to find the normal modes, we need to consider only the spatial equation. Consider only the spatial equation. And apply the boundary conditions. Okay, so I'm going to rewrite the boundary conditions in terms of phi and psi, but I'm then going to show you that you can just skip right ahead always. So let's start with the left boundary condition. For the left boundary condition, we have u of 0, t must be equal to 0. This is equal to psi of t times phi of 0. And since psi is just a function or set of functions of time, if it's equal to 0, then that tells us that we then have a trivial solution. So let's write this out actually. So from this, either psi of t must be equal to 0 or phi of 0 is equal to 0. And so simply psi of t equal to 0 is a trivial solution. So it is a solution, but it's a trivial solution. So then thus, we get that psi of 0 must be equal to 0. So that's our first boundary condition in terms of phi. If we now do the right boundary condition, in this case we get u of L, t is equal to 0, which then is equal to psi of t times phi of L. And we see the same thing here. We have that either psi of t is equal to 0 or phi of L is equal to 0. So psi of t is a trivial solution. And then thus we get that phi of L is equal to 0. Now you can always skip. Once we do the separation of variables, we can always just skip to the fact that phi of L, actually let's do phi of 0 is equal to phi of L, and both are equal to 0. So we can always skip ahead to this. So once you have the differential equations, you can then skip down to this. If you don't feel comfortable skipping, you can go ahead and just plug in like we did here for each boundary condition and then determine what's going on as a result of that. Okay, so let's rewrite our solution for phi. We said that phi of x is equal to r times the sine of omega over cx plus q times the cosine of omega over cx. Now I kind of switched the cosine and sine orders between, if you look at the psi equation, we started off with cosine, and then we had sine. And then in the phi equation, we end up with sine first and cosine second. The order does not matter in this. And then we also have the two boundary conditions. So we have phi of 0 equal to phi of L, and they're both equal to 0. And so what we now want to do is go ahead and apply the first boundary condition. We always want to apply the boundary condition at phi of 0 first, if we can, because that will usually allow us to eliminate something. Now, if you have a spring or a mass at the end, then things are a little bit more complicated. But if you have a fixed boundary or a free boundary, in that case, you always want to apply phi of 0 first, because it will allow you to eliminate one of the terms. Okay, so we have phi of 0 equal to, or let me rephrase that, you should always apply the boundary condition at x equals 0 first, because it will allow you to usually eliminate one of the terms. So in this case, we're going to get r times the sine of 0 plus q times the cosine of 0. The sine of 0 is 0, and the cosine of 0 is 1. And so then this is then equal to q, and it's equal to 0. Therefore, we get that q is equal to 0. And then from that, we will find that now phi of x is simply equal to r times the sine of omega over cx. And so we've been able to now eliminate that q because we applied the boundary condition at x equals 0. If we applied the boundary condition at x equals L first, we would have ran into the problem of not being able to eliminate one of the sines of the cosine terms, and then you would end up with two unknowns still rather than finding one of those unknowns. Let's now apply the right boundary condition. So phi of L is equal to r times the sine of omega over CL, and again that's equal to 0. So in this case we have that either r is equal to 0 or the sine of omega over CL, that is equal to 0. So r equal to 0 is a trivial solution. Thus, we need to go with that the sine of omega over CL, that is equal to 0. Okay, so we have that the sine of omega over CL, this is equal to 0. That tells us then that omega L over C must be equal to plus or minus n pi, although we are only going to consider positive in this case. So plus or minus n pi for n equal to 1, 2, 3, so on. And then this tells us that the natural frequencies omega sub n must be equal to n pi times c divided by L, and again true for n equals 1, 2, so on. And so in this case, we can write that this represents the countable infinity. This represents the countable infinity of natural frequencies. So if you're a little hung up on what countable infinity means, it means that there are an infinite number of natural frequencies. However, we can count them. So we can assign them to the natural number. So we will have the first natural frequency, the second natural frequency, the third, and so on, all the way up into infinity. So there's an infinite number of them, but we can count them. So that means that that infinity is less than an uncountable infinity. It's less dense, we could say. And with that in mind, the natural frequencies are ordered as omega 1 is greater than 0, which is less than omega 2, less than omega 3, and so on. And we will call omega 1 here. This is the fundamental frequency. So the fundamental frequency is the lowest frequency of all of the natural frequencies. Okay, so with that in mind, then we can write that each natural frequency let's say omega sub n corresponds to an eigenfunction. And again, the eigenfunctions are also called mode shapes. And those will be phi sub n of x will be equal to some constant that we don't know, r sub n times the sine of omega n x over c true for n equals 1, 2, 3, so on. Now, usually you would go ahead and mass orthonormalize these to find that unknown constant. In this class, we're not going to do that. We're reserving that for an advanced class on advanced vibration. So you do not need to mass orthonormalize, and you're not expected to do that on any of the exams. And so we'll just say then that hence the infinite set of normal modes is, so again, a normal mode has two things. First, the natural frequencies, and in this case that is n pi c over L, and the eigenfunctions or mode shapes phi n of x is then equal to, we'll leave it just as Rn times the sine of, we'll plug in omega, and then we'll eliminate the c, so we'll get n pi over L times x. And this then is true for n equals 1, 2, 3, and so on. And so then this is actually the answer to this problem. These are now the mode shapes that we were looking for, or the normal modes of vibration. At this point, we could then go ahead and plot the mode shapes. Let's go ahead and do that, although we weren't asked to. Let's go ahead and do it for at least the first two modes. So in black here, let's draw the, so this is the two ends of the spring, or of the string. And that is the undeformed configuration. So then our first mode shape is just going to be half of a sine wave, something like that. At the top here with an X, we have what's known as an antinode. That's a position of maximum displacement. The edges are then nodes. The second mode will be a full sine wave with a node in the center. So in red here, this is known as a node. And then we have two antinodes. And so those are what the first two mode shapes look like. Let's just write out what a node is. This is a position of 0 displacement. And then an antinode is the opposite of that. Let me write that a little bit better. So an antinode is a position of maximum displacement. Okay, and that is it for this example.